Hello, this video is on the construction of quotient vector spaces. It is a technical construction, but it takes its place because it is convenient. It is convenient mostly for more or less theoretical purposes, interpretations of solution sets of linear systems, and some other things. So let's start with a pair, a subspace in a vector space. And with such a pair we can define an equivalence relation on the ambient vector space. And I will be using the notations of congruences just to emphasize the similarity. The definition of this equivalence relation will be very similar to congruence of integers modulo some fixed number. So two vectors are congruent or equivalent with respect to this relation, congruent modulo u, if and only if their difference belongs to u. So that is a definition. Of course, one has to check that this relation is indeed an equivalence relation. But that is straightforward, follows from the properties of a subspace and is delegated to you. Equivalence classes become a way of separating the vector space into disjoint union of subsets. So equivalence class of a vector v from the vector space v by definition is this. It's a sum, or rather the set of all possible sums of v, and v is fixed in this story, with all possible vectors from the subspace. So as usual with equivalence relations, the whole set on which this relation is defined is a disjoint union of cosets. But the cosets are labeled by vectors, but only some vectors. So let me look at this kind of small dimension example. Imagine that v is dimension 2. So that will be an example, and the subspace is dimension 1. Geometrically I can imagine the plane, visualizing my v, and a line through the origin which is my u. And equivalence classes in this case will be geometrically lines parallel to u. So any vector we take, a vector v, the equivalence class will be the line which passes through the endpoint of v and is parallel to u. And of course the whole plane is stratified, is a disjoint union of such parallel lines, and every vector is in one of them, but there are many vectors on each ending on each of those lines. So that is an illustration of this disjoint union. We're still labeled by vectors in v, but some vectors we have to choose representatives to see cosets uniquely. So the first statement about this set of cosets, so the set of cosets of equivalence classes is denoted as usual v modulo u, or and is called the quotient of v by u. The first statement is that this quotient is in a natural way vector space. And moreover, the quotient map, which just takes a vector and assigns to it its coset, is linear. So we have two statements in one, but that is the naturality of the of the vector space structure on the quotient. It is natural in the sense that this natural map, which is defined no matter what, is linear. So let's see how we can make this space linear so that the map will become linear. And that is all determined. To have this map linear, we have to preserve the addition and the scalar multiplication under this map. So we have to really follow the structure of V, linear vector space structure of V, to tell us what the vector space structure on the quotient should be, and that's what it is. So two cosets, if we want to add them, some other vector, we have to be consistent with addition in V before taking the coset, so that's supposed to match with this sum. And scalar multiplication, again, supposed to be aligned with scalar multiplication before computing cosets, and it should have this property. And this property is translated into the equivalence relation. They just say that if we take, well, these properties have to be really the properties of subsets, right? This subset plus this subset, so this is the sum of subsets. So we take any pair of elements from these two and then compute the sum, and it should be always any subset. So that's what these properties say on the nose. But please verify that they are equivalent to these two properties for congruence relation we start with. So if we have two pairs, W prime congruent to W, not U, then we have two conclusions: that sums of these congruent vectors are congruent, and then if you take one pair and then scale, then scalings will also be congruent. So that is what it takes to have these two properties. Again, they're equivalent, and these are kind of easy to check. You could just use the definition and use the property of a subspace, the property of subspace U, to verify them. So that is the meaning, deep meaning of the quotient space. We define some equivalence relation, which is sort of natural, and then we observe that the quotient map can be made linear if we define a vector space structure on the quotient. And so first immediate application, sometimes called as the first isomorphism theorem, says the following. So let's start with a linear map between two vector spaces, call it phi. So that is a linear map. And as a map, it can be decomposed into an injective map from the image and the surjective map onto the image, which is still phi. And that is just the standard decomposition of any map, linear or not. But what we can immediately see, that the image is a subspace, so this is linear, so that is a subspace of the target of the map. And now we have this kernel construction at our disposal, sorry, not quotient, and we can take the quotient by the kernel, because the kernel is also a subspace, and we have this map which just knows about the kernel. As soon as we have the subspace, we run the story and we end up with a quotient, and we have the quotient map. So this statement of the first isomorphism theorem is that we can close up the loop. There is a natural identification between the quotient by the kernel and the image. And this isomorphism works as follows. Again, if you look at the picture, the composition supposed to match with the original map phi, so there is no freedom but to take an element in here, which is this coset, this subset of V, and map it into the value of the linear map phi on any representative. So it should be correctly defined. It should not depend on whatever choice for the representative here you make. And indeed it doesn't, because any other element in this subset is a sum of that V and something which is annihilated by phi. So using linearity of phi, you can see that the answer is all the same. Well, the application which immediately comes to mind is the following. So if we just take a case of coordinate vector spaces, the linear map between two such, we know that such linear map is always given by matrix multiplication. So then the image of such linear map is what is called the column space of A. Well, you could check that columns of A are in the image, and anything which is in the image is linear combination of them, so that's why. The kernel is called the null space of A. It's everything which is annihilated by multiplication with A. And then if we look, say, at this equation for some vector in the target, it is nothing but the system of linear equations with matrix A and then the column right hand side B. So it is solvable if and only if B is in the image, which is the column space of A, and then solutions can be obtained in this way. So if it is in the image, then, well, there is something in the source which is mapped, so some partial solution, and then all other solutions will have to have this shape, and that will be the coset of x0 by the kernel, by the null space. So that is that's supposed to remind you of the general answer for the solutions of an inhomogeneous system here. You have a partial solution, and then you have solutions, all possible solutions of a homogeneous system, and that is all that you have here. So that is solving systems of linear equations in a quick few lines using this cosets with this equivalence relation. So another example is also a theoretical nature, but rather small in scale. Let's imagine two linear functions on the same vector space V. So the values are in the ground field F. Let's assume that both are non-zero, so they are linear, and then their kernels are the same as a subspace. So these are, for non-zero linear functions, these are codimension 1 subspaces of V, and we assume that they're the same. So under this assumption, we should always have the following relation, that linear functions are proportional with some proportionality coefficient which has to be non-zero. And yes, the quickest way, in my opinion, to justify this implication is to use the first isomorphism theorem. So in this case, the image of these linear functions, just by the definition, is the same one-dimensional coordinate vector space, the base field itself. So we have the square collapsing, these sides are the same, and we have the square for both of our linear functions, which are linear maps. We have the same middle term, the quotient by the kernels are the same, and this map doesn't know anything about linear functions, it only cares about what they kill, about their kernels. And then there should be some freedom at the last step, which is identifying these two vector spaces. So that's what linear functions will control, but these are one-dimensional vector spaces, so only freedom in choosing such identification is scaling up with a non-zero scalar. So that's why if we have decomposition for one, then decomposition for the other will only differ in this step, and that is what this scalar multiple is representing. That's it. See you later.